Let's begin considering simple classifiers. A binary classifier is a function which can decide whether or not an input vector belongs to a specific class. Binary classification often refers to two-class classification. It's a type of linear classifier which makes its predictions based on a linear predictor function. Examples are perceptron, Adeline, logistic regression, and support vector machine. These are artificial neurons. Neurons are interconnected nerve cells involved in the processing and transmitting signals. They can be summarized in this figure. Signals will come to the neuron through dendrites, and the cell body will integrate the signals. Then the accumulated signal exceeds a certain threshold, then an output will be made. That's the schematic description of a neuron. Here we have definition for binary classifier. Xi, Yi are labeled data set, and with X in RD, it is d-dimensional, and Y is either 0 or 1. A binary classifier finds a hyperplane in RD that separates data points into two classes, as in this figure. So binary classifiers will find such hyperplane to separate the data set into two parts. Labels. We chose labels 0 and 1 are chosen for simplicity. You may choose some other values, -1 and 1. You can choose them. A hyperplane can be formulated by a normal vector and a shift and W0, so that hyperplane can be written in this way. For that line in 2D, the line is a hyperplane, and W is a normal vector of the line. Okay. To learn W and W0, you may have to formulate a cost function to minimize. This formulation is the sum of squared error. Error squared are summed. So it is called the sum of squared error. And now for this input, this one is called, that one Z, is called net input. And many cases, we try to use certain activation function, so that after activation, the value is compared with a given label, and we try to minimize this objective function. Let's go to the Perceptron algorithm. The Perceptron is a binary classifier of supervised learning. It began in 1957 from Cornell Aeronautical Laboratory, and later on it is refined, and then here even it is implemented as hardware. And that means that once input came, then immediately through a filter, and immediately output came out. This is a definition of the perceptron as a binary classifier. X is input values, input vector, and W is weight vector that must be trained during the training. And here we'll choose two class labels, 1 and -1. You can choose 0 and 1 or -1 and 1. Either way, you can choose labels. Now, once input values and weights are here selected, then now we try to get net input. That is, weight the sum of input values with these weight values. Now, in activation in the Perceptron, we are using a thresholding scheme. Once the Z net input is larger than or equal to theta, or threshold, then the value is 1. And otherwise, we get -1. So after getting this activation value, and we eventually try to minimize that. Once we chose W so that it is completely separating the data set into two parts, then now this activation will make for every point here, superscript I is indicating the ith data point. So if once W is chosen accurately, then that for all I, the value must be 0, so that the sum of squared error must be 0, and it's done in training. Okay. So along with this activation, and we try to get the value and compare with the label. And once it is wrong, then through iteration, we try to update. Okay. Now, here for simplicity, rather than this theta value, we may try to move the theta to left-hand side, so that, and move this one, and then here we define Z in this way, so that sometimes we yet writing in this form, but practically thereon. And for this one now, because it is moved to left-hand side, rather than theta, and we are using 0, so that for activation, once it is larger than or equal to 0, then activated value is 1, otherwise -1. In the literature of machine learning, the variable W0 is called the bias. So sometimes we are using the letter B to indicate the bias. But here, W0, the equation equals 0 represents a hyperplane, and W0 decide the intercept. Okay, then I'm using here now M, but that must be D. Okay, okay. Here we have Perceptron learning rule. The Rosenblatt's initial perceptron rule is given in this way. In the beginning, we initialize weight to 0 or small random numbers. And for each training sample xi, we try to compute the activation value, that is predicted level value, and by using that, we try to update the weight. The practical update rule is here. For W, and to get new W, start from old one, and we try to get this correction vector. The correction vector is obtained in this way. To measure the difference, this is original label, and that is predicted label from here. And now xi the data point is now multiplied by this one, and then again scaled by eta. We have to choose eta small, and along with this, correction vector is updated. For W0, what's the same, but now we are without this xi, we try to update W0. Here, eta is called the learning rate, and yi is the true class label, and y hat I denotes the predicted class label. Okay, for this update, let's try to do a simple thought experiment. Let the perceptron predict the class label correctly, then yi minus yi hat must be 0, so that the weights remained unchanged. Once it's wrong, then here this one can be is 1, for example, then it's minus 1, then it will be 2. If it is minus 1, if it is plus 1, there must be minus 2. So that this whole thing is the same as here, plus minus 2 eta x, so that the weight wj is pursued toward the direction of the positive or negative target class. So that once it is not 0, then along with this one, and try to push the hyperplane so that try to locate the hyperplane between the classes. Okay. Here we have a program, Perceptron PY. I implemented this class for Perceptron. In the beginning, okay, now you have to give dimension of x, the data points, and initial epoch is 10, and running rate is 0.01. So you can assign these values, or you can use this default, but that is necessary in the beginning. Now, along with input, that is initialization, self-epoch is defined, and self-learning rate and self-weight open initialize the 0 weights. Here in class, start with self. The prefix self means that these variables are shared in every function's method in the class. So here, once you call activate, and along with a point, then the point will be here dot product along with weight, and once during the iteration weights are updated, then the last updated weight will be used to get dot product and W0 added. So it is net input. Once that input is larger than 0, then return 1. If not, then return 0. Right now we consider label 1 and 0. That is now fed. This is a training operation. X train, Y train are given. Then here number of epoch. So K epoch is executed. And in each epoch, and from X train, Y train, each point, each label is selected. For that one, activate by using last updated weight, and here that's activated, and this is a predicted Y value. And by using exactly the formula, we try to organize this correction vector and correction term for W0 and added to weights. So in each iteration, it is updated, and next iteration will use the updated value. And automatically, it is shared in this function activate. Now predict, and start with y hat empty, and all test data points, and you may get, okay, either this way and that way you can implement. So from empty y hat, you append the activations, activity value for each x in x data set. You can implement it this way, or and you commit that one and use that one for x in x test, and you can here append each activation, or you may write down in separate 2-line. Python is quite flexible. You can write in various ways. And also this score function is counting the correct answers and start from 0. And once for each xy in x test, y test, and after activation, that is activity value is the same as the label value, then we count and add it by 1. After counting all of the corrected answer and divide by length of the number of points, then we can get accuracy in percentage. Right? These are major functions in most of classifiers. Okay, now here I added one more, that is fit and feed, and weight all. Start with this one and try to get here appended the weights. That is for figure purpose. So that is change, modification of fit function. Only, okay, this one is added, and then that line is added and return. So in main program, we want to see how weights are changing and how the hyperplanes are changing to converge to a certain final hyperplane. Okay, so in reality, you don't have to implement this portion. Okay. Now that is the main program calling Perceptron. We are using iris dataset. We start with NumPy package and plot. And here from Scikit-learn, we'll try to use now. Okay, that is train test split, and also from Scikit-learn, we get dataset. And here, that line is for printer out, and for engineering number, for example, sometimes you see 0.0000 e to the 0. Rather than that, and along with this option, you can get 0 dot. So it's very simplified. So I'm using this option most cases. Now we import the Perceptron implemented. Okay, for that one, from dataset, we choose iris dataset. From there on, we collect data into X, and now along with the target key, we can get here now numeral, the labels. The label names are not 0, 1, 2. There are 3 classes, so that it will include 0, 1, 2. But here, and basically, they have some target, practical target name, and also the futures, 4 columns. And this is a 4-dimensional data set, and you have original future names. Okay. Now for the data, you may now here try to get the number of data points and the dimension, and also for y, we consider as a set that is only 0, 1, 0, 1, 2 are remained, and length will be 3, so that you can print out to see how the data set is given. And from the data set to test the perceptron, we need a little bit simplify the data. So we try to choose two classes. So from X, just we try to get only the portion where y is less than or equal to 1. So y equals 0, y equals 1. Two classes are selected. Also for y, the labels, we collected them the same way. And again, now, once you selected the two classes, then again, yet it has 4 columns. It's 4-dimensional data set. Out of that, we try to choose the first column and the third column to get 2-dimensional data set. Okay, after selecting that one, now for x2, y2, we try to split by using the function x to y2 with the train size 0.7, and that will make this separation. And here we open the perceptron classifier, and now this object is made along with dimension. It is required, and dimension, and that is optional. We chose epoch is 2. The perceptron is updating the object, the weights for each single data points. So number of iteration is the same as the number of points. So epoch means go through all data set twice. So that is enough. And you can call for the classifier fit, but rather than fit, we try to use fit and fig so that we get weights all. And accuracy can be obtained by calling the scoop method, and you can print out. For that one, output, the accuracy is 1. Now, you may try to get predicted values for each test point, and you can save that, but here is commented out. We don't have to call here. Now, below portion is for figuring. I eliminated it, and we see here figures. That is for two-dimensional, two-class data set we made from here. That one. And now perceptron is initialized with 0, that, and then after 10 iteration, after passing using 10 data points, it becomes that line. And now after using 20 points, now it becomes that one. After passing 30 points, it came here. And this hyperplane will make every point the right prediction, so that after that, and it is not moving. But here, this one is a little bit near to these points. So once it is done around here, and that is, it can be this line, it can be that line, or a bit different slope like that. Anyway, among these lines, once the perceptron reaches at one of these lines, then never move. So that depending on your initialization and depending on your choice of the learning rate, your final, even though it is converged, and your final separation line is different, so that it's not really ideal classifier. However, once a given data set is separable, like in this subset of areas, and once it's separable, then a certain number of iteration later, you can get right separating hyperplane. Even though it is not optimal, you can get it anyway. That's the property of the perceptron algorithm. Okay, that's the end of part 1. Thank you.